signals are first quantized and then encoded. So in order to get the complete digital signal, so we need to use a quantizer and an encoder along with the sampler. And this is actually the fundamental concept of pulse code modulation. The basic operations required in order to convert a signal into completely digital signal, a sampler, a quantizer and encoder are required. Now, let us see what is quantizing. Quantizing means it is an approximation. It does the quantizing, approximation to the original signal. Quantizing refers to the use of a finite set of amplitude levels and the selection of a level nearest to a particular sample value of the message signal as the representation for it. So this operation is combined with the sampling permits the use of coded pulses for representing the message signal. And the quantizer signal is an approximation to the original signal. Here, the quality of the approximation may be improved by reducing the step size, thereby increasing the number of allowable levels. So, as the step size is reduced, the number of levels will be increased so that the noise will be reduced, the quantization noise will be reduced, so the quality of the approximation will be improved. So, we will discuss in detail about the quantization process. So, the limitation of communication system for communicating over long channels is noise can enter anywhere along the channel. So, this situation can be modified by subjecting a signal to the operation of quantization. Let us see what is the operation of quantization, how we can do the process of quantization. Now, for this one, let us consider a message signal M of t. So, this is a message signal M of t whose excursions is conformed to the range VL to VH. So, that means the two peaks are VL and two extremities are VL and VH. So, which is defined as the dynamic range of the message signal. Now, divide this total range into m equal intervals. So, the total range of this message signal has to be divided into m equal intervals. So, each of step size s. And now this step size is defined as VH minus VL by m. M is nothing but here levels. M represents the total number of levels. So, since we have divide the range into m equal intervals, the step size is equals to the dynamic range divided by the total number of levels. Now, in the center of each of these steps, in the center of each of these steps, we locate the quantization levels M0, M1, M2, M3, M4, M5 and so on. Now we have to generate the quantizer signal, so which is defined as, represented as MQ of t. So first, the dynamic range of the message signal is VL and VH, and here it has to be subdivided into m number of levels, and based on that one, the step size has to be fixed as dynamic range by number of levels, and then in the center of each of these steps, we need to locate the quantization levels M0, M1 and so on, M2. Now we have to generate the quantizer signal. Let us see how to generate the quantizer signal. Now each of these levels, since initially we have done m number of levels, and each of these level is represented by delta naught, delta 1, delta 2, delta 3 and so on. So the first step in generation of quantizer signal is you have to identify the range at which m of t lies in. So whenever this m of t is nothing but your message signal. Whenever this message signal is in the range delta naught, the signal MQ of t maintains the constant level m naught. It maintains the constant level m naught. That means from this particular point to this particular point is delta naught. M of t in the range delta naught. So this is the message signal where it lies in the range delta naught. So whenever this m of t in this particular range, the signal MQ of t maintains the constant level m naught. If you see this one from this particular point to this particular point, the analog signal from this point to this point, m of t is in the range delta 1. So it maintains, the quantized signal maintains a constant level m1. In the similar fashion, whenever m of t is in the range delta 2, mq of t maintains a constant level m2. Similarly, we have to approximate, we have to take all the values. We have to approximate all the values based on the range of m of t in which it basically lies in. Therefore, always the signal MQ of t will be at one of the levels m0, m1, m2 and so on. So in this particular case, we have used 8 number of levels. So MQ of t will be at any one of the m0 to m7 levels. So if the m0 of t is in this range, it maintains this constant level, m0 level. If it is in this particular level, m1 is in this particular range, then it maintains m1, level m1. Similarly, we have to take all the levels. We have to take all the values for m of t. And now here we have to observe one thing, the transition in MQ of t from m0 to m1. So this is the transition, right? The transition in MQ of t from m0 to m1 is made abruptly when m of t passes the transition level L01. So when m of t passes this transition level L01, then the transition in MQ of t from m0 to m1 is made abruptly. So which is actually the midway between m01 and m1, m0 and m1. So L01 is midway between m0 and m1. So where the transition, an abrupt transition takes place. Thus the signal MQ of t makes a jump of step size s. And MQ of t has the value of quantization level to which m of t is closest. Okay, so it is approximated to the closest level, closest value. It is approximated to closest value. And if you see, each level is separated by step size s. So all the levels are separated by step size s. And this separation of extremities VL and VH, if you see VL and VH, this separation is its nearest quantization level s by 2. So this separation is s by 2 here. For VL, the separation is s by 2. And also for VH, the separation is s by 2. And for all the remaining levels, the step size is s. The step size is s. So you can easily observe from this figure. At every instant, we have to find the deviation of MQ of t from M of t. So if you observe, all the values which are from this particular point to this particular point is approximated to level M0. So this is approximated to M0. Therefore, at every instant, the quantization error M of t minus MQ of t has a magnitude which is less than or equal to s by 2. So there exists a quantization error, the deviation from the original signal. The quantized signal is somewhat deviated from the original signal. And this deviation is known as quantization error. That is, the difference between M of t minus MQ of t is known as quantization error, and it has the maximum magnitude. It has a magnitude which is less than or equal to s by 2. So the maximum quantization error is plus or minus s by 2. And we can observe that the quantizer signal is an approximation to the original signal. So in this way, so we can approximate the signal. We can approximate the signal. And the quality of approximation can be improved by reducing the step size. So if you reduce the step size, what happens is the quantization error reduces because more number of levels comes into the picture. So that the number of levels will be increased. So the approximation is towards its closest value. Hence, the difference between m of t minus mq of t reduces, though. So quantization error reduces. Therefore, the quality of approximation improves. So the quality depends on the step size. So reducing the step size, which improves the number of levels. But if you reduce the step size to a very small value, human eye may not be able to distinguish the original signal from the quantized signal. Okay, but this is good, but so if you reduce the step size to a very small value, the number of levels will be increased, so that the number of bits required to transmit each sample is increased. So obviously the bandwidth is going to be increased. So suppose if you consider the number of levels used in color TV, it is 256. So 256 means it can be expressed as 2 to the power of n. So 8 bits are required to transmit each sample. But 64 level gives fairly good color TV performance. So 64 means 2 power 6, so that the number of levels can be reduced and the number of bits can be reduced. So bandwidth requirement is reduced. So care must be taken to maintain the quantization error and the number of levels and the number of bits to represent each of the level, each of the sample. And this type of in this type of quantization, the step size, if you observe the step size, it is constant. The step size S is fixed for the entire process. And this type of quantization is defined as uniform quantization. So it has linear operations, linear characteristics. And now coming to the classification of uniform quantizer. Since here, as the step size is fixed, it is defined and mid-rise type of uniform quantizer. Mid-rate type of uniform quantizer and mid-rise type of uniform quantizer. So these are the quantizer characteristics for mid-rate quantizer and mid-rise quantizer. So if you see these two characteristics, the quantizer characteristics have a staircase shape irrespective of whether it is a mid-rate type or mid-rise type. The only different characteristics, the origin is in the trade position, and that is why it is called mid-rate uniform quantizer. See here. So this is the origin is in the trade position, whereas in mid-rise quantization, the origin is in the rise portion of the staircase type of characteristic. See, so the origin is in the rise portion of staircase type. Therefore, it is defined as the mid-rise type of quantizer. So if you see the mid-rate type, any input value between minus 0.5 to 0.5 is mapped to an output value of 0. And any input value between 0.5 to 1.5 is mapped to an output value of 1, and so on. Whereas in mid-rise quantizer, any input value between 0 and 1 is mapped to an output value 0.5. Any value between 0 to 1 is mapped to 0.5, and any input value between 1 and 2 is mapped to an output value of 1.5 and so on. So this is the basic difference between mid-thread type and mid-rise type of quantization. And the number of levels in mid-rise type of quantizer is like uniform quantizer only. That means L is equals to 2 to the power of n. L is equals to 2 to the power of n. Okay. So the levels in mid-rise quantizer is L is equals to 2 to the power of n, whereas the number of levels in mid-thread quantizer is L is equals to 2 to the power of n minus 1. N minus 1. Now, let us see the coding. So first sampling operation and then quantization, and next one is the coding operation. So coding is, it translates the discrete sequence of values to more appropriate format of signal, and the process of converting binary data to digital signal. So it converts the binary data into digital signal. So let us see how the coding can be achieved with an example. So for example, let us consider the message signal m of t. So here the message signal m of t is taken, whose amplitudes varies from -4 to +4. Whose amplitudes, that means the dynamic range is this one. So it varies from -4 to +4. And since the range is -4 to +4 is divided into 8 levels, which are known as quantization levels, the step size is 1 volt, because the step size is equals to VH minus VL by M, where M is equals to 8 and 4 minus of -4, 8 by 8, which is equals to 1 volt. Therefore, the step size is 1 volt. Now, the pulses having values from -4 to -3 are approximated to a value -3.5. So -4 to -3 are approximated to a value -3.5, and -3 to -2 are approximated to a value -2.5, and so on. So this is the quantization process. So when quantizing a signal m of t, which creates a new signal mq of t. So this mq of t is created. So which is an approximation to m of t. And afterwards we need to assign some code numbers to each of these levels. For example, we assign code number 0 to a level -3.5. So since we will approximate all the values which lies between -4 to -3 to be approximated to -3.5 volts. And this -3.5 is assigned to a code number 0. And we assign a code number 1 to level -2.5. And we assign a code number 2 to -1.5, and so on. So in this way, we will assign the code numbers to each of the levels after approximation. So each code number is represented in binary format. Now each code number is represented by binary format. So suppose for n levels are there, n binary digits are required to represent it, where m is equals to 2 to the power of n. Okay, so that means if m is equals to 2 to the power of n, that means the number of levels in this particular case are 8. So these 8 levels can be represented by means of 2 to the power of n. That means each sample is represented by means of 3 bits. 3 binary digits are used to represent each sample. Now if you observe the first sample, so whose sample value is 1.3. This is 1.3. So this 1.3 has to be approximated to its nearest quantization level, which is equals to 1.5. Since all the values between 1 and 2 are approximated to 1.5. So this 1.3 is approximated to 1.5. And a code number 5 is assigned to 1.5. Therefore, the binary representation of this 5 is 101. Similarly, at this particular sample, the sample value is 3.6 and this 3.6 is approximated to its nearest quantized level, which is 3.5 here. And the code number assigned to 3.5 is 7. So this is 7. And the equivalent binary representation is 111. So in this particular case, the sample value is 1.3, nearest quantization level is 1.5. And the difference is 0.2 words, which is defined as quantization noise in that particular level. Similarly, here the quantization error is 0.1 and here the quantization error is 0.2, and for all the things we need to calculate the quantization error. And now we have to represent the binary digits by electrical pulses, because this has to be transmitted over the channel. So this binary digits has to be represented by means of electrical pulses. So from this one, these are the binary representation of all the samples. And this binary data is converted into electrical pulses. That means the presence of a pulse is represented by 1. That means 1 is represented by means of presence of pulse. 0 is represented by means of absence of the pulse. And there is a time slot. If you see 111, there is a time slot allotted to each bit, a portion of which is guard time. So which is defined as the guard time. This tau g indicates the guard time. So in this way, the binary digits are represented by means of electrical pulses, because it is the effect of noise implementation will be less, and also it will be for security purpose we'll use this thing, electrical pulses, to represent the binary information. And in the previous example, we have used the binary code. So suppose if there exists a 16 number of levels, then each sample is represented by means of 16 can be represented as 2 to the power of 4. So each sample is represented by means of 4 bits. And we can use gray code also. So binary code or gray code also we can use. We can use different types of codes in order to represent the binary information, the encoded information.